Well, thank you all for joining us today. It is my pleasure to introduce Maila Hallare, presenting on number theory meets dynamics, oscillators with 2-Adic forcing.
Thank you, Gavin. Um, Thank you, Pushpi, Maxine, and Brian for coming to my presentation. So before I start, I just want to say that in this in this project, I created a new or ordinary differential equation not too long ago, around November or December last year. And what I like about it is that number one, it is quite simple. Number two, even though it is simple, it comes from a constant coefficient ODE with a very simple forcing. The dynamical behaviors are fascinating. And number three, um, the analytical solution can be computed using elementary methods. And of course, MATLAB can easily produce simulations. So here we go. Number theory meets dynamics, oscillators with 2-Adic forcing. Again, my name is Maila Hallare, and I teach at the United States Air Force Academy. Thank you, as always, to Brian and everyone at Simayodi for always being open to my crazy ideas in math. Okay. Oops, sorry. So, like what I said earlier, I created an ODE and I have searched maybe 1 or 2 weeks or a couple of days spread over 2 weeks. And I tried to check the literature to see if anybody has done what I have created here. And nobody has done something like this. So it is it's quite simple and it is um, a good demo of an intersection between number theory, real analysis, and ODEs. So the premise is quite simple. So consider this second order constant coefficient differential equation with this forcing on the right-hand side. And this forcing on the right-hand side is the 2-Adic valuation of the ceiling function. And here we consider t to be non-negative. So this symbol here is the ceiling function, and then we will talk about the 2-Adic valuation shortly. Um, so unlike the classical forcing functions, this right-hand side is comes from number theory. This is an example of an arithmetic function. So it introduces a hierarchical stepwise excitation to the system. So let us first talk about the ceiling function. So the ceiling function is sometimes known as the rounding up function. Here, we know that for any t is always bounded in between two consecutive integers. So the ceiling of t will be equal to n, wherein t is between n minus 1 and n. Okay, so that's easy, rounding up. How about the 2-Adic valuation? So this is the arithmetic function that I mentioned earlier. This comes from the area in number theory called p-adic analysis, as in p as in prime. So for p equals 2, then we get the so-called 2-Adic valuation. It basically measures the divisibility of an integer by 2. So the definition says that the 2-Adic valuation of n is the largest integer such that 2 to the k divides n. Okay, so let's take a look at some example computations of the 2-Adic valuation. So the 2-Adic valuation of 8 will be equal to 3. And why is that? Because when we write 8 in its prime factorization, 8 is 2 cubed, and 3 is the largest power, or 3 is the largest coefficient of 2 in the prime factorization of 8. So V2 of 8 is 3. Another example, the 2-Adic valuation of 12 will be equal to 2. Again, just write 12 in its prime factorization. And finally, the 2-Adic valuation of any odd integer is equal to 0 because any odd integer does not have any power of 2 in its prime factorization. Okay, also known as the fundamental theorem of arithmetic. So having known that, so we have the ceiling function and then the 2-Adic valuation. Let me just do a little bit more examples. So here in this table, we have our t's on the first row and then we take the 2-Adic valuation on the second row, and then we see the we see the ceiling on the second row, and then we see the 2-Adic valuation of the ceiling of t. And so we have these numbers. By the way, the 2-Adic valuation of 0 is defined to be infinity. So let's take a look at some examples again. So the 2-Adic valuation of 4.1, round up 4.1 to the ceiling 5, and the 5 is an odd, therefore 2-Adic valuation of the ceiling of t is 0. One more example, maybe for any number between 13 and 14, the 2-Adic valuation would be 14, but 14 has only one, 14 is 2 times 7. And so this shows us furthermore, I mean, this table shows us that there is no simple pattern in the 2-Adic valuation of a number. And I also hope you see that before computing the 2-Adic valuation, I had to take the ceiling function first, because the 2-Adic valuation is defined only for integers. Okay, so now we know how to analyze or how to interpret the forcing function. So again, let's look at our goal. Our goal is to consider this constant coefficient second order non-homogeneous differential equation with this arithmetic function as our forcing function. So we would like to know what will be the behavior of the solutions for such an ODE. Also, well, because my training is in pure mathematics, I spent some time trying to find the closed form or the analytical solution of this differential equation. And as we know from our ODE classes that because we have something non-homogeneous or inhomogeneous, then the general solution can be expressed as the sum of the complementary function and the particular solution. So for the complementary function, which I label here as YH, we know that there are 3 cases to consider depending on the characteristic equation of our ODE. So this is when the discriminant of the characteristic equation is positive. This is when the discriminant of the characteristic equation is exactly 0, and when the discriminant of the characteristic equation is negative, also known as the underdamped case. In other words, our energy will be focused on computing the particular solution of our differential equation. So this is the result. Well, there's a lot more. I did not have space to type them all, but for this initial value problem, the particular solution can be written in this way, wherein h here is the Heaviside function, and Gn is an inverse Laplace, which you will see shortly. Okay, I've also decided to write the particular solution in this form so that it is what we call in the form by Duhamel, or the Duhamel's principal form for solutions to differential equations. So the details are in here. So the particular solution looks like this. And let me just show you the proof. It's not that bad. So a sketch of the proof goes like this. So as you can see, I have chosen Cauchy initial values. In other words, standard initial conditions. I have tried solving this ODE using some other initial conditions or boundary conditions. I think many of the ideas will just transfer. Also, because I used the Cauchy initial conditions, I wanted to prepare everything for the Laplace transform method. So as before, given this inhomogeneous differential equation, we take the Laplace of both sides. Because this is second order, we know that in the transformed variable s, we will have quadratic in s. So we now solve for y of s here being the Laplace of the solution y of t. So the Laplace transform method allows us to transform the given ODE into an algebraic problem. I have a typo here. The plus should not be there. So anyway, in the end, after taking the Laplace, given these initial conditions, we now have our y of s. And according to the Laplace transform method, in order to find the y of t, we will go back to the time domain. So we only need to take the inverse Laplace after this step. Okay, and so once we look at this y of s, I have separated that into blue and red. Okay, the blue here will capture the complementary function, and this part here will be the particular solution. And so the specific solution is given by this. And as we have seen earlier, this part is already known. So we will focus our energy on computing this, the inverse Laplace of V of s over as squared plus bs plus c. So the as squared plus bs plus c in the bottom comes from the fact that we have a constant coefficient second order differential equation with coefficients a, b, and c. Okay, so the V of s here, I'm using the standard notation that the Laplace of the little or the Laplace of the lowercase is equal to uppercase with s as our transformed variable. So I have some students, I think, in the audience. So I will go a little bit slow here so that you can understand some. This one would be a little bit of real analysis, but it's not that bad. So how do we compute the Laplace of the 2-Adic valuation of the ceiling of T? Okay, so here, this is called the characteristic function. The characteristic function gives two values only, either 1 or 0, if if the input comes from the domain n minus 1 to n. Otherwise, the output of this characteristic function is 0. So it's like saying if you are part of this set, then you're a go. If you're not part of this set, then you'll be a 0. Okay, so because of this definition of the characteristic function, we can now write the 2-Adic valuation of the ceiling of T as this sum. So we are going to pick up those coefficients V2 of n as we march through as we march through T after chopping it up into unit intervals n minus 1 to n. Okay, so having written our 2-Adic valuation of the ceiling of T in this form, now it's time to compute the Laplace. And from our ordinary differential equations days, we know that when you're computing the Laplace of any function, you bump it with our kernel, which is the exponential in this case. So given this function, bump it with respect to the exponential, and then take the integral from 0 to infinity. Okay, so this line here tells us the 2-Adic value, tells us the Laplace of the 2-Adic valuation of the ceiling. Okay, this part here obviously requires a little bit more work. Okay, and so because we have expressed our 2-Adic valuation as a sum, we replace this by this sum, and so you will get the integral of a sum. Now there is this magic theorem. Not magic. I don't want to I don't want the students in the audience to think that there is math is magical. Anyway, there is this theorem in grad school. You will learn about in grad school called the Fubini's theorem. The Fubini's theorem is a theorem that will allow you to interchange operators. So notice here that that V of s will become the integral of a sum. And then you apply this theorem called Fubini, and that will allow you to interchange the sum with the integral. So the point is, this will now be the Laplace of the 2-Adic valuation of the ceiling function. A little bit more cleaning up, and we will be there almost. So because this is now the Laplace of the characteristic function, but the characteristic function, remember, is either a 0 or a 1. It will become a 1 if the t belongs to this interval. So this improper integral can now be reduced into this integral, which is easier to solve. Yep. So now we are in our happy place in calculus 1 because this one can be solved by the fundamental theorem of calculus. So this integral can be solved in this way. Plug in the top, minus plug in the bottom. In the end, that will be our integral. So the next step is just cleaning things up. So plug and chug what you have computed before. So the 2-Adic valuation, the Laplace of the 2-Adic valuation of the ceiling is now equal to this thing. Okay, so now we have our coefficients, V2 of n, and this expression here coming from the Laplace. And then a little bit more cleaning up. Notice that on this side, you can factor out e to the negative Sn. Okay, once you do that factoring, the remaining factors will be in terms of s. Because those will be in terms of s, you can take it outside the summation. Whew, okay, so we are now done. Well, you can do a lot more as I did. I tried to compute more things on this, but this will be a good stopping point for our 2-Adic, or for the Laplace of the 2-Adic valuation of the ceiling of t. Now we plug in that expression over here. And in other words, all we need to do now is compute the inverse Laplace of that. So again, we have this inverse Laplace of this expression with a summation. This does not really require Fubini because this will give us a Bromwich integral. Here it's a little bit simpler. You can just use the linearity property. So you can put this back in, and then you have a summation. Well, yeah, a little bit of real analysis there because this is an infinity. Anyway, in the end, when we rearrange our expression, we will get this. So notice that in the inverse Laplace, we have this e to the negative Sn, but we have a property for Laplace that says the inverse Laplace of any function f bumped with an exponential can be expressed as a translate of f multiplied by the Heaviside function. And so you just plug and chug. In the end, this will be our expression. Oh, thank you for your patience. I really enjoyed solving the closed form of the solution to the ODE because it requires like a little bit of number theory, a little bit of real analysis. Now let's go to the fascinating part, thanks to MATLAB. Okay, so what I will show next are pictures, lots of graphs. So here, let's consider an overdamped case. What I did was, so for each of the three cases, well, I included a fourth undamped case, I just put in a classical second order constant coefficient non-homogeneous differential equation with a classical forcing function, and then compare that with our special forcing here. So look at this nice picture on the right. But first, let's look at the left. Because we have the overdamped case here, okay, the homogeneous part or the complementary function looks like this with modes or characteristic values -2 and -3. And we know that the YP or the particular solution will give us the steady state oscillation in the long-term behavior. But look at this right-hand side. I will pause for effect about 3 seconds because this is really the fascinating part. Okay? Because using the traditional forcing function, you cannot see such a behavior. To guide your eyes, I put in these these red dashed lines to tell you where the peaks happen. So for example, this peak in the behavior of the solution occurs at 128, which is 2 to the 7. This peak here occurs at 64, right? And 64 is 2 to the 6. This peak here occurs at 32, and so on and so forth. So this time we see oscillations, but unlike before, these are irregular oscillations. You can see something like this for nonlinear oscillators, a little bit artificial. You have to make it appear, but this one comes from our simple linear ODE. This is an example of an underdamped case. So here, the discriminant of the characteristic equation is negative. So the complementary function looks like that. And like before, we have steady state oscillations. So the picture for our special ODE looks like this. Again, some structured peaks. This is an example of a critically damped simulation. So here we have repeated roots And so the complementary function looks like that. And I have this picture. Oh, sorry, there is a typo here. The parenthesis should be after the t. So when the forcing is a periodic forcing, such as cosine of 2 pi t, then this would be the steady state. This would be the long-term behavior. Okay. And again, we see the structured peaks here. Now, get ready for the next picture. So we saw the overdamped, the underdamped, and the critically damped. From our ODE classes, the next interesting thing happens when you have an undamped case. Okay, so there will be no first derivative term. Look at that. The left-hand side is a resonance. Okay, so we see here that we have unbounded linear growth in amplitude. Okay, so when the frequency of the driver or the forcing function matches the natural frequency of the system, then observe here that the magnitude of the solution or of the response is growing in an unbounded way. Okay, we also call this as resonance. Look at what we have for our special forcing function. There is some kind of resonance here, but we see that, like the resonance case, there is a buildup of energy over time. So I say here it's a classical resonance-like behavior because there is something special going on here that I am still in the process of uncovering. Okay, but this is a nice, beautiful result coming from our ODE. Okay, so here I have computed some resonance conditions. So we say that there is resonance in our system when the natural frequency aligns with the dominant frequency of this. Because our forcing function is not your typical periodic function, right? The natural the resonance can be determined by looking at the dominant harmonics of your forcing function. So in here, one has to apply a little bit of Fourier analysis. And in my initial computations, there are so-called dominant harmonics and then the supporting harmonics. But what I have shown you is the strongest resonance, and it occurs when C is 4 pi squared. Okay? Because of that observation, when we don't have when we don't have damping at all. So notice that there is no y prime here. So this is an undamped second order constant coefficient differential equation. Okay, this is where we would expect some resonance if parameters are okay. Okay, so with f of t equals this, our classical forcing, then we will have this closed elliptical orbit in the phase space. So basically what happens here is that we need to convert the second order ODE into a system of two first order ODE. And then you plot on the horizontal the y, plot on the vertical the velocity or the y prime. Okay, notice the corresponding phase space for our differential equation. So here, instead of having a closed elliptical orbit, we have some expanding spirals here. And this actually suggests that there is some kind of resonance because remember at powers of 2, we have energy injected into our system. Okay, so this is when C equals 4 pi squared. Again, when you have the classical forcing, you have unbounded resonance growth. And when you have our 2-Adic valuation, we have this structured stepwise manner. Oh, I am done. So here, this is a summary of some of the things that I have presented today. I have actually a longer list of things to do to analyze this simple ODE, which is again an intersection of ODE, of dynamics and number theory. So for my students, I am planning to give them some opportunities to understand the frequencies better. And maybe this one can be, well, because as we know, for some classical nonlinear oscillators, we can see chaos. And I am I am imagining that with a classical nonlinear oscillator with a 2-Adic valuation as a forcing, then it'll be fascinating. And of course, applications. Oh, thank you. I am done. Thank you all.